Aloha, is there truly such a thing as an objective system for evaluating social or academic contributions? Or are all systems, no matter how well designed, inherently vulnerable to manipulation and gaming? These questions are at the heart of ongoing debates about the fairness and effectiveness of research metrics. Many universities strive to enhance their reputations by climbing higher in global rankings. One common criterion in these rankings is the Faculty Research Productivity Index, which includes metrics such as the total amount of research grants, the number of published research articles, and the average citation count per faculty member. In research-intensive institutions, faculty members are under significant pressure to publish as many high-impact journal articles as possible to secure promotions. This competition has even become a matter of national pride. According to Digital Sciences Dimensions database, researchers in China authored nearly 830,000 papers in 2023, accounting for approximately 15% of the world's 5.4 million articles. By sheer output, China has surpassed the United States, emerging as the global leader in research productivity. While numbers are often regarded as objective measures for evaluation, problems arise when these metrics are treated as rigid or absolute standards. In such cases, individuals or institutions may manipulate the numbers to achieve favorable outcomes, a phenomenon described as Campbell's Law or Goodhart's Law. In academia, the impact factor is widely accepted as an indicator of a journal's prestige, calculated based on the number of citations received by its articles. However, this metric has also been subject to exploitation. To inflate their impact factors, some journals require authors to cite articles previously published in the same journal as a condition for accepting their manuscripts. Additionally, some universities differentiate between teaching-focused instructors and research-focused professors in their faculty roles. In one extreme case, a university converted all teaching-focused instructors to contract-based adjunct positions. This decision was driven by the belief that these instructors, who are less research active, negatively impacted the institution's citation per faculty metric, thereby harming its standing in rankings. These examples underscore how an overemphasis on numeric standards can distort academic priorities and lead to unintended consequences in the pursuit of institutional prestige. It is important to recognize that every metric carries inherent biases, as bibliometrics, being a social construct, reflects the values and priorities of our society. One frequently criticized bias is the tendency of the academic publication system to reward conformity, which can disadvantage scholars pursuing risky or highly innovative research that may not align with conventional standards. For example, for a long time academic journals have been preferring empirical research conducted with traditional statistics to those analyzed by data science methods. With this in mind, it is clear that no metric is entirely foolproof. Each comes with its own set of trade-offs. In the following discussion, I will examine the strengths and weaknesses of various metrics. A common metric for assessing research productivity is the number of publications accepted by peer-reviewed journals. At first glance, this approach appears straightforward and reasonable. However, a closer examination reveals significant shortcomings. First, this metric prioritizes quantity over quality. For instance, John Nash, a towering figure in game theory and mathematics, published only 23 papers throughout his career. While this output is modest compared to many academics, the groundbreaking quality and lasting impact of his work far outweigh the number of his publications. Second, this criterion narrowly focuses on peer-reviewed journal articles, excluding other forms of scholarly contributions such as books and book chapters. In a study on research productivity by Cadez, Dymowski, and Groff, faculty publications were extracted exclusively from the Web of Science Core Collection database, omitting books and book chapters. The researchers justified this decision by noting that faculty often prioritize publishing in journals indexed by Web of Science to meet promotion requirements. Indeed, some universities disregard books and book chapters when evaluating faculty research portfolios. However, Adhering strictly to this reasoning would undervalue many seminal works. For example, Thomas Kuhn's The Structure of Scientific Revolutions and John Tukey's Exploratory Data Analysis are landmark publications that revolutionized their fields, yet they would not count under such a narrow metric. Similarly, Kent Keel published a book chapter documenting the development of the first mobile functional MRI scanner for studying psychopathy in prison populations. Although this chapter had a transformative impact on neuropsychology, it would be overlooked by metrics that discount anything outside peer-reviewed journal articles. In addition to the number of publications, bibliometrics also measures research impact based on the number of citations, because citations reflect the dissemination of knowledge and how influential the articles are. There are different citation indexes in the market, such as the H-index, the I-10 index, the number of highly influential citations, and the research interest score. The H-index, introduced by physicist Jorge Hirsch in 2005, is reported in several productivity and citation tracking sites, such as Google Scholar, Semantic Scholar, ResearchGate, Web of Science, Scopus, Digital Sciences Dimensions, and so on. It is noteworthy that both Google Scholar and Semantic Scholar are enabled by artificial intelligence-based search engines, making it more powerful than conventional databases. Specifically, both citation tracking sites automatically scan the internet for research products and then categorize the results by relevancy. By comparing Google Scholar against various conventional databases, especially the Web of Science, Halevi, Moed, and Bar-Lan concluded that Google Scholar is more comprehensive than other databases. However, many academic institutions and funding agencies still prefer traditional databases like Web of Science and Scopus. One of the major merits of Google Scholar is its inclusiveness. Unlike the Web of Science database, Google Scholar covers various types of scholarly contributions, including journal articles, book chapters, white papers, and even online papers, while the H-index in Semantic Scholar includes journal articles, reviews, meta-analyses, letters, commentaries, clinical trials, editorials, news, case reports, and datasets. Additionally, there is a widespread complaint that some metrics do not take the order of authorship into account. As a remedy, the H-index assigns more weight to articles written as the first author, and the fractional contribution of the co-authors are weighted accordingly. However, citation counts could create certain unfair situations. For example, while an article written by a physicist is mostly cited by the peers in the same field only, a methodological article might be widely cited by scholars in different fields, because researchers in medicine, natural sciences, engineering, and social sciences who conduct data analysis need methodological references to support the method choice. More importantly, the H-index could be artificially manipulated. For example, Robert Sternberg, a prominent psychologist known for his work on intelligence and creativity, faced criticism for excessive self-citation. In 2018, while serving as editor of Perspectives on Psychological Science, concerns were raised about the high frequency of his self-citations in articles he authored for the journal. An analysis revealed that in 7 papers published over 2 years, approximately 46% of the references were self-citations. Taking a lesson from Sternberg's experience, I'll be careful not to overly cite my own work. Instead, maybe I should ask my family members, clients, friends, colleagues, and students to cite it for me. Just kidding. To remediate the problem, ResearchGate adjusted the H-index by taking self-citations into account. Like many other metrics, there is no acceptable cutoff for the H-index. Rather, it varies from discipline to discipline. For instance, a 2015 study indicates that among the top 25 social work and psychology programs in the U.S., the average H-index for social work faculty was 6.62, while psychology has more than doubled, 15.67. Nonetheless, one could not draw a hasty conclusion that psychology faculty are more productive and influential than social work faculty. While the H-index is used by Google Scholar, Semantic Scholar, and ResearchGate, each one has its own unique features. In addition to the H-index, Google Scholar also reports the I-10 index, which is the number of publications with at least 10 citations. Semantic Scholar has a similar feature known as the number of highly influential citations. The score of highly influential citations is a remedy for superfluous citations. It was argued that authors may cite papers out of courtesy and thus raw numbers of citations could be misleading. As a countermeasure, Semantic Scholar utilizes AI and machine learning algorithms to identify the subset of a paper's citations in which the paper had a strong and meaningful impact on the citing work, based on a number of factors, including the surrounding context of the paper. However, this treatment is by no means 100% foolproof because slight variations in spelling of last and first names would result in misattribution or misidentification. ResearchGate was founded in Germany by two physicians and a computer scientist in 2008. Besides the H-index, ResearchGate provides users with a metric known as the Research Interest Score. This metric combines reads by unique ResearchGate members, recommendations, and citations, excluding self-citations, to offer a comprehensive view of how researchers' work is engaging the scientific community. However, its validity is questionable because ResearchGate members' interaction can be intentionally inflated. I hope the preceding analysis underscores a crucial point. There is no such thing as truly objective assessment. Every metric reflects subjective social values, influenced by what people prioritize as important or less important. When university administrations focus on boosting institutional rankings, they place immense pressure on faculty. This dynamic is encapsulated in the long-standing phrase, publish or perish. In prestigious universities, the stakes are especially high. Some assistant professors fail to secure tenure even after 10 years if they cannot meet the rigorous research productivity standards. Consequently, faculty may resort to whatever means necessary to publish as many articles as possible. One prevalent but problematic practice is p-hacking, conducting numerous statistical tests to produce a significant result, often at the expense of rigorous methodology. Unfortunately, some faculty members even commit unethical practices and research misconduct to publish. This raises a critical question. How many of these publications truly contribute meaningful knowledge to their respective fields? In the rush to meet numerical targets, the emphasis on quantity over quality risks undermining the integrity and value of scholarly research. Not everything can be fairly quantified. Is it time to rethink our research metrics? Thank you for watching. Mahalo.